All right, welcome back, physicists. Today we're going to take a look at the different kinematic equations that you can use to solve problems. So first, let's just do a quick review on sort of the what we call the kinematic variables. So big picture, we talk about the ability to measure an object's position as a function of time, its velocity as a function of time, and its acceleration as a function of time. Right? And so obviously we then would include time as that fourth variable. Now these are the things that we can graph, right? And these are usually the things that change over time or are different from situation to situation. But the other thing that we can think about is what is the starting value for each one of these three things, right? What is the x position when t equals 0, the velocity when t equals 0, and the acceleration when t equals 0, which we can turn into shorthand as x initial, v initial, and a initial. Now, usually the acceleration is not going to change as a function of time. So in our kinematic equations, we'll just see it as a. We also could then ask the question, what is the position at a later value of time, the velocity at a later value of time, and again, the acceleration as a later value of time. But like I said, it's usually just going to remain a constant, whether it's 0 or a number. And so we could think of this second position as x final and the second velocity as v final. Again, it's just a shorthand for saying what is the position at this later value of time, not when the time equals 0. So let's see. We have potentially three different equations that describe the position, velocity, and acceleration as a function of time that should need to include information about where does the object start, how fast is it going at the start, and is it accelerating. So let's write down those three equations to start. So for acceleration as a function of time, this one's kind of easy. We expect the acceleration to just remain a constant. So this is not an equation that shows up on the reference table, but the idea is that the acceleration as a function of time just looks like a horizontal line. Next, we have the velocity as a function of time. It is the acceleration multiplied by the time plus the initial velocity. And then we have the position as a function of time is 1/2 a t squared plus v initial t plus x initial, right? And all of these equations are the equations that would describe the equation of the line of that particular kinematic variable, right? So again, we've got the acceleration as a function of time. We have the velocity as a function of time. And we have the position as a function of time. And again, depending on whether any of these three starting numbers are positive, negative, or 0, result in a different shape of the graph. We also have two kinematic equations that try to take the time out, right? We're not going to go through the details on how to get these two kinematic equations, but as you might anticipate, if we have two equations with two unknowns, it should be possible to combine these equations as we need to in order to get here. These are equations that are given to you on the reference table. The first one has to do with velocity. V final squared equals V initial squared plus 2a. And sometimes I'll call it delta x, or it can also be called d. And this is just x final minus x initial. So the way you want to think about this one is sort of a graph, right? Where we have v final and we have sort of x delta x on the bottom here. right? And that's sort of the graph that we're talking about. You'll notice it does not have time in it. It relies on acceleration and your change in position, and then your starting value here is the initial velocity squared. And then the second equation tells us that delta x equals 1/2 v final plus v initial times delta t, right? And the kinematic variable missing here we didn't have time, here we don't have acceleration. If, however, the acceleration is equal to 0, then this part here is just equal to v initial, because that v initial plus v initial divided by 2 would just give me v initial. So this is an equation that you would only really use if the acceleration is not equal to 0. Otherwise, you just end up with this equation here. And that's the last thing I want to leave you with is, while these are the two equations, the two main equations that we start out with, you can get certain versions of it when you plug in your initial conditions, we call them. What is the initial position, velocity, and acceleration as a function of time? And the best way to get good at using the kinematic equations is just to practice solving them, right? For each individual kinematic equation, it's possible if you have one thing unknown and all the other things unknowns, that you could solve for it. So check out the homeworks to see some different examples on how to do that. Thanks for watching.